Good morning, and thank you all to be here. I'm Rohit Damankar, and this is my colleague Rob King. I work for Tipping Point, and I'm a manager for digital vaccine service at Tipping Point, and Rob is a security researcher at Tipping Point. So today, Rob and I are going to talk about how we can do identification and analysis on protocols based on these statistics. So our brief agenda for the day is, first we want to talk to you about why we are exploring this route of trying to identify protocols using their statistical metrics. And one of the examples which we have been extensively studying is Skype, and we will talk about the various coordinates or the various statistical coordinates that we are using for this analysis. And towards the end, we'll also talk about what further work we want to do and the framework which will be available for download from our website. So jumping straight in, the reason for trying to do identification of protocols and trying to look at other ways of doing it is there are at least 3 or 4 problems that are becoming common. So first of all, what we are seeing is a rise in encrypted traffic, and especially the traffic which you would like to ideally block. What we are seeing is malware and botnets have now started using encryption and obfuscation. So it's not an easy job to just look at the packet content and be able to identify the bad part of it and stop these packets. The other thing which we have seen is ports like 443, the SSL 53 DNS, they are open on most enterprises. And what you normally see is these ports are now being also used for covert communications. And in many cases, the traffic which is traversing on these ports really does not look like SSL or DNS traffic. And we want to find a way in which we can identify that bad traffic from good SSL or DNS traffic as an example. And thirdly, we all have used peer-to-peer protocols at some stage, things like BitTorrent for downloading entire Linux distributions, or things like Kazaa, Nutella, LimeWire, BearShare, you name any, there's a big list of them, for downloading music and video files from the internet. And what we are seeing now is even these protocols are changing from first generation to the next generation. The first generation of these protocols did not use any obfuscation or encryption techniques to avoid detection. But now when you see things like Skype, they are purposefully trying to put in obfuscation and encryption so that network-based systems cannot detect these. And that's a problem which we are trying to solve here. So one of the things which is very common with peer-to-peer protocols is they try to hog a lot of your bandwidth. So if you go to a typical university and the dorm environments, almost 60 to 75% traffic could be these peer-to-peer protocols. And as a result, your mission-critical protocols like emails and maybe Oracle databases, your web servers, are not able to use that bandwidth. So with the first generation of these protocols, what has been happening is network-based systems have been able to uniquely fingerprint them, and there are multiple systems which are available out there that can go and rate shape these protocols. And now in their next generation, that is the exact things these protocols are trying to avoid. They don't want to get fingerprinted, and they don't want any kind of system to be able to see them, either block them or rate shape them. So before we dig into more on the statistics, let's look at just a few simple examples of the first generation peer-to-peer protocols. And an example here is the Kazaa traffic. And what you are seeing on the screen is a request which goes from one of the Kazaa peers to another Kazaa peer for downloading a file. And if you look at this request, it looks just like a standard HTTP protocol with the hash of the file being downloaded going in the URL of the protocol. And also, if you look at the HTTP headers, it clearly contains the word Kazaa in that. So there are at least two HTTP headers which are containing the word kaza. And so if you want to identify a packet belonging to kaza, it's a simple task because you know the kind of URL the protocol is using, and you also know that the headers contain the word kaza. So in this case, it's an example where the first generation peer-to-peer protocol is just using the standard HTTP protocol, except you notice that the ports are all in high ranges. This is another example of another peer-to-peer application called eDonkey. eDonkey and eMule are very popular peer-to-peer applications in Europe. And in this case, what you see on the screen is a hex dump of the packet. And this is the request packet, which again goes for downloading a file from one eDonkey peer to another. The thing to note here is this protocol is more proprietary. It's not using a common protocol like HTTP or FTP. But if you see a lot of these kind of packets, you can figure out exactly how eDonkey or eMule is working. You will normally notice that the first byte of any request download starts with a byte E3. The next 4 bytes in the packet are actually the length of the data in the remaining part of the packet. And for people who frequently look at hex dumps, if you look at the last 2 lines, they are actually clear text, and that's the clear text representation of the file being downloaded. So once again, this is another example of a proprietary protocol which you can fingerprint using a network device and be able to stop or rate limit. And now coming to the latest example of Skype. Skype does an excellent job in trying to hide detection. As soon as you open your Skype clients, first of all, you will see a lot of packets going on TCP as well as UDP ports. Most of these packets go to high-numbered ports. And the only way we have been able to identify the Skype traffic belonging to a video or a voice communication is to figure out where the maximum data is flowing. And when you are recording packets and as you are talking at the same time, figuring out which particular UDP session is being for transporting the voice traffic. And again, even if you look at a lot of Skype traffic, what you find is the content of the packets is random. Of course, Skype client and server, they understand that. But for an external user, the content is totally random. Even when you initiate the call between the same 2 parties, in a span of few minutes, what you will notice is the port numbers are totally changing, the length of the packet totally changes, as well as the content too. So using the conventional tactics, it's very difficult to identify this particular protocol. And that's why what you need here is a shift where so far we have been relying on detecting these using content embedded in the packets. And what you ideally would like to go to for some of these newer protocols is to go for a framework, if possible, by exploring the statistical properties. The closest analogy I can think of is if you are given hydrogen and a helium jar, the gases, and if you're supposed to identify which of them is hydrogen, which of them is helium, one way of doing that is to study the electron properties of both the gases using their whatever lights they emit under particular, when you shine a laser and the kind of light they emit, you can figure out which is hydrogen and which is helium. And that kind of detection is more like based on the physical properties of the gases themselves. But however, another detection is also possible where you put these jars of gases under different pressure and different temperatures and see how the volume changes. And that's exactly the kind of paradigm you're trying to now bring to protocols, where you're observing the gross properties of these protocols compared to the minor or minute properties. And this is a quote which I like from one of my earliest statistics classes, where it says statistics is like a bikini that reveals what is interesting but hides what is vital. And after the class, this is the only thing I remember. So what we are trying to see here is if both interesting and vital things can be revealed via this analysis.
Are you driving for the slides?
Yeah.
So I don't want to alarm anyone, but I'm wearing a wire. So I also get to have the fun job of explaining the drunk guy, which I think is supposed to be a cartoonish representation of me. But it is an important statement in that this is statistics here. Statistics are like guesses. They're not definite. PISA is never going to say, this is definitely DNS, this is definitely Skype, this is definitely eDonkey. But it is going to say, I can tell you with quite a bit of probability that this is DNS or Skype or eDonkey or one of those protocols. And the way we do that is we actually measure these protocols on various axes. In fact, 10 different axes, 10 dimensions. And we get to use nice phrases like plotting a point in a 10-dimensional hypercube and things like that, which makes me sound really smart around the office and then just gets blank stares from everybody else. Any blank stares? Everybody's blank staring. Okay, that's good. Off to a great start. So let's look at the first coordinate that we track, and that's the average packet size to client. So not only are we looking at the packet size, we're looking at the directionality of the packet. And in this case, client and server are sort of arbitrarily defined. You can identify the client or the server during training via IP address or port or what have you. And this is always important because, if you have large packets going in one direction and small packets going in another direction, then you're definitely doing some sort of client-server interaction. The client is requesting something of the server is sending something back, things like that. Whereas on things like streaming protocols, you're going to get massive amounts of packets, but they're going to be very, very small. And if you're doing file transfers, they're going to tend to be very, very large. And that's a very good way of distinguishing between two different types of protocols. And all of these points, all these axes were chosen because in many ways you can't avoid doing it this way. You have to do it this way. So even if you try to obfuscate what you're doing, you're still going to see these properties. And so if we can go. And so what we have here is a graph that we've shown, which is the average packet size to client over time. And we've got the blue points, which is just other traffic, and we've got the red points, which is Skype. And as you can see, the Skype stuff clusters very, very well. You don't see any packets over 400 bytes in size, and you see most packets within the 200 and smaller range. And of course, that's necessary for things like VoIP because you have to have very small packets. Very big packets take a long time, and if you drop a really big packet in a voice traffic, you get an uncomfortable pause. So, oh, that was clever. I came up with that on the fly. So. And then the next one is the average packet size to server. And everything I said just then for the client makes sense for this as well, except that we're looking at it in the other direction. And something that's really interesting is we're working on ways to identify which one we think is actually the client or the server by looking at the average packet size, going in both directions. And so obviously, certain things, if you see something that receives like 1 or 2 bytes on a PC, on your office network, it receives just a very small packet and then suddenly sends a huge amount of traffic, probably not a good idea. It's probably saying, give me all the passwords that you know about Mr. Keylogger. And Mr. Keylogger wakes up, sends all the passwords, and then goes back to sleep. Definitely a bad thing. We want to make sure that we can track that sort of thing. So we picked that axis as well. And then now we're looking at the packet size to server. This is the same graph. And once again, we've got Skype in red, and we've got everything else in blue. And once again, Skype, very interestingly, has almost the exact same distribution in the alternate direction. And that's because it's a two-way voice communication protocol. It can't help but have the same packet size in both directions because it's, 2 people talking. Unless you're talking to, like, my girlfriend, in which case it's 1 person talking. But anyway, she's not here, so I can say that. So as you can see, once again, we don't have any packets over 400 bytes. And we have most packets, in fact, the vast majority of packets in Skype, under 200 bytes. So once again, you see a very nice clustering of packets, versus other protocols. And once again, Skype is just being used as an example. We actually have some other examples with other protocols later showing, that all protocols tend to cluster in a certain way. And then finally, now we have the average inter-packet delay. And this is the amount of time between 2 subsequent packets in one direction, specifically from the client. And this is once again going to be one of those things where streaming protocols like VoIP or video are going to have a very, very small inter-packet delay because they want to make sure the next frame of video gets there. They want to make sure the next word in the sentence gets there. Whereas it doesn't really matter so much. If your web page is delayed by 2/3 of a second, nobody's really going to complain. But if you all of a sudden have voice traffic dropping or video frames dropping or audio frames dropping, then you have a real problem. So once again, a lot of protocols can't help but run this way. They have to have a very small interpacket delay. And other things have to have very large interpacket delays. If you're doing something like, say, XML RPC, that takes a very large amount of server-side processing because, you have to parse the XML, you have to do all this, you have to do all that. And so it's going to be slightly slower than, say, a regular HTTP request or something like that. So you can cluster that as well. And if we can go to the graph, you can see once again that Skype, very, very, very banded. We have those packets up at the top there. Those were actually the initial setup packets, and those were sort of, they took a little time to get there. But then almost all of the packets band into a very, very consistent amount of time. And that is very important. That's not just that they're small, it's that they're consistently small, that they're in the same sort of area. You don't want to have one packet come very quickly and then one packet come very, very slowly and then one packet come in the medium, in the middle. You want to have it as the machine is ready to receive the next packet is there. So you need to have predictability. And that's something that, once again, it can't be avoided. If you're doing a streaming protocol, you have to have something that bands like that. So if we can go to the next slide here. And then this is the same coordinate, but in the alternate direction. And once again, everything I said for that, everything I said for that applies here as well. You can't have just arbitrary times in very many protocols. Whereas some protocols, you might have intentionally unusual timing. That's something that's trying to avoid detection. And once again, that's going to look completely random and is going to differentiate it from another protocol. And that's also very, very important. And then this is the graph. And as you can see in the other direction, this is without the packet. We don't see the session setup here. And so all of the packets band very, very well because they're flying very, very quickly and very, very consistently for voice traffic. And then this is traffic difference. And this one takes a little bit of explaining. So aren't you glad that you have me here? Traffic difference is basically what the ratio is between the two parties. Is one party sending significantly more traffic than the other party? Are they roughly the same? Things like that. And once again, if you have massive amounts of traffic in one direction, you're probably looking at a client-server relationship. Whereas if you have a bunch of packets in both directions and the ratio is roughly 1-to-1 or somewhere very close to that, you're definitely doing some sort of bilateral communication. And so once again, that's something that's very useful to identify a protocol. You're not going to see, for example, encrypted HTTP having a lot of traffic in both directions. You're going to see very large amounts of traffic in one direction and very small amounts of traffic in the other. And so if we, excuse me, we can go there. So as you can see, Skype, because you're tight. Skype is, this is hard to see in two dimensions, but that's actually relatively linear because you've got one side talking, and then one side, and then they stop talking for a while, and they talk, and they stop and they talk, and you get this very nice linear progression over time of the difference between the two parties in traffic. And that would actually be easier to see in a 10-dimensional graph, but unlike Rohit, I only see in 3 dimensions. So, and now we have the variances. And these are all treated as separate coordinates. And these are the standard deviations for all of the coordinates. So like you have the standard deviation of the packet size to client, the standard deviation of the packet size to server, the standard deviation for interpacket delay, both client and server. And that way we can see if things tend to be very, very random or if they tend to fall in a fairly normal distribution. And that's something that is, once again, very useful to identify a protocol. If you have a bunch of packets that fall in a very narrow range and don't tend to fall out of that range, you can assume certain characteristics about that protocol. So if we want to go there. And this is Rohit's favorite coordinate, so I'm going to let him talk about it. So I'm going to hand it back over to him.
So the Shannon entropy is used in the information theory for trying to figure out how random a data is. And the same concept is actually also used for figuring out how to compress data. And the way you define this entropy, the mathematical expression is if you have a series of outcomes, if you have an experiment and there are outcomes x1 to xn with probability p of xi, what you do for finding the Shannon entropy is take the product of each probability with its log to the base 2 and sum over all your data set. For our case, what we are doing here is when we see these protocols and the packets, we try to take a dynamic probability of what characters are up occurring in the packets. So what we do is, once we have seen 3 or 4 or 5 packets, we will compute a histogram of the character and its frequency. And that particular histogram we use for computation of the Shannon entropy for that protocol. And to get an intuitive feel of what this number is, let's assume that you have a protocol which is just sending a bunch of A's in all the packets. So for such a protocol, your probability of character A is 1 because that's the only character occurring in that protocol. And therefore, if you take log of 1, which is 0, your Shannon entropy comes out to be 0. And again, that is intuitive because this protocol is not sending any random data. And if you were to compress this particular protocol, all you could say is how many times the number of A's are happening in the packet. So I don't need to send, like let's say the protocol is sending 5 packets, each 1500 bytes worth of A's. To the other end, if I want to compress and send the same information, I can just send a character 7500, a number 7500, and because the protocol is not random. And that's why it allows for an easy compression. Similarly, let's say if you had another protocol where character A and character B occurs equally likely, each of the probability is half, and once you compute the Shannon entropy for that, you get a number of 1, which tells you saying there is some randomness, but it's really not totally random. And what is the maximum entropy you can get from the character set which we are using is if you have letters from or characters from hex 00 through hex FF, and they are all equally likely in a protocol, implying the protocol is totally random because any character from null to hex FF is occurring with equal probability, you get the max Shannon entropy, which is probability for each letter is 1 over 256, and once you take 1 over 256 log of 1 over 256 times the whole thing 256, the answer is 8. I mean, you can do the math. But in our case, therefore, the entropy is bounded between the values 0 and 8 for any protocol which we have seen. And if you see for Skype, right from the beginning, on the y-axis is a scaled entropy, which I'll talk about later, and on the x-axis is the number of packets. You see the entropy for Skype is at its maximum right from packet number 200, implying that it's using very random data or encrypted data, which is the characteristic of that. So for training purposes, we had collected a lot of data. And since we were actually initially focusing on Skype as an example, we tried to collect a lot of data for Skype. There's another voice or IP application called Gizmo, not as popular as Skype, and a lot of UDP traffic like DNS, NTP, NetBIOS from both the corporate and some of the university environments. And we tried to make sure that there was enough variation in the samples we were collecting. So we made Skype calls within the same office. We made Skype calls within the same city. We come from Austin, so we made calls in Austin. We made calls within the United States, and we also made international calls from to India, where I come from. And that gives us a good amount of deviation in the data. So that makes our data set very rich. Just one thing to kind of keep in mind with the data set is we didn't go and explore things like dial-up links. So all the interpacket delays which we were experiencing are all typically on broadband or LAN environments. So that factor of dial-up environment is not taken into account for this data set. The other problem we faced is if you look at all the coordinates, some of them are measuring packet sizes and some of them are measuring times. And both of these things are on a totally different scale. Typically your packets, the maximum you can have on a LAN is 1500 bytes. I mean, you can have jumbo Ethernet frames for 9000 bytes or so, but in our case we didn't have any of those. And on the other hand, the interpacket delays, they are all in milliseconds or fractions of milliseconds. So what we had to do was, to be able to make sense of the data while plotting it in this 10-dimensional hypercube, we had to scale the coordinates. So everything was scaled to a maximum, and we took the maximum as 2000. So all the entropy was scaled to 2000, as well as all the interpacket delay, they were all scaled to a scale of 2000. And that's what you see on all those graphs where the max was around 2000. The other interesting thing which you already saw from the Skype graphs is if you let 200, 400 or 600 packets pass by, the statistics quite stabilize. So all the coordinates what we are seeing, either they try to get to a single value asymptotically or they fall in distinct bands. And all the other traffic also has the same characteristic, where either they asymptotically stabilize to a standard value or they have very little variation in the set of values.
And now it's back to me. I'm sure you all missed me very much. So as Rohit said, we did scale all of the coordinates, but that's not all we did. And what we're going to talk about now is that, we've got all this data, we've got this massive data, and we've statistically analyzed it, and we've massaged it and everything, but now what do we do when we want to identify a completely random stream, one we've never seen before? We want to compare it to that huge dictionary or database of pre-trained data. And so the way the data format works is you have for every packet, say for packet 0, packet 1, packet 2, packet 3, you have a list of packets, and this is per protocol, a list of packets with the statistical information for each training set. So you have this massive data set where the first packet of this protocol in this stream is this, the first packet of this protocol in the other stream that we train with is this, and so on and so forth. And then we do that for every one. And the statistics are calculated for every packet. And the reason, the statistics are calculated for the entire stream up to that packet. We do some clever tricks to avoid having to recalculate things, but when you look at, say, offset 4, you're talking about the entire stream, how it looks as of packet 4. And we do that because we want to make sure, we don't want to say, see the first SYN and the first ACK and say, oh, that's Skype, of course, Skype does SYN ACK. So that obviously doesn't work. It also is no good, really, because it doesn't do SYN ACK. But anyway, so once we get all this in this big cube and we do everything, then we have two distance metrics that we use. The first one is the normalized or scaled Euclidean distance. And that's your standard high school geometry Euclidean distance, except that it's extended into 2 dimensions instead of 3. And it's also scaled and then averaged. So we take a point, we define a point for the unknown protocol in that space, and then we take its distance to every other point in the protocol we're testing against, and we do this for every protocol we're testing against that we know about. And then we take the averages of the average of all those distances, and we say, okay, what has the lowest distance? And that's the lowest distance. And we hold that, and then, if we can go, next slide, please. Then we go and we take the Mahalanobis distance. And this was one of those things that is just all sorts of fun, great fun to code. And the Mahalanobis distance was described first by P.C. Mahalanobis in 1936. Very, very bright guy. And what it does is it is a scale invariant distance metric. And it also can handle things where, say, a training set is not spherically distributed around the mean. It does no good if your training set looks like this. You take the average Euclidean distance. This is still in the set, but it's way over here, and this one's way over here, and your point's over here. It doesn't work very well. The Mahalanobis distance, instead of testing the actual position, it tests the covariance, or how much the variables tend to change together. So, if we can. So what you do is you build what is called a covariance matrix. The covariance matrix, and I'm going to get into covariance a bit more in the next slide. You take this covariance matrix and you use that as a weight for the average distance to all these other points. We still take the distance to all these other points and we average them together, but we weight that average with this covariance matrix. And once again, we're not actually talking about a specific coordinate in this case. It's not in a geometric sense. It is actually in a covariance sense. And you can see all sorts of fun math there, and it's no fun for me to actually read it to you because that you can read it yourself. But it's a really, really cool protocol metric, and I really hope you guys look it up later. If that's the only thing you take away from this talk, that would be worthwhile. So if we can go one more. So covariance, that's the big deal for Mahalanobis distance. If you say something like, say you have the inner packet delay, and you have the packet size, and you note that as the packet size increases, the inner packet delay also increases, takes longer to send. And so what you have there is a positive covariance. And then say, for example, you have something where it starts to go down, and the other thing goes down as well. That's a negative covariance. And then say you have something, and this is the always fun one, where the two variables are completely independent. One goes up, one goes down. You have no covariance. It's a zero covariance. And so when you have this covariance matrix, and this covariance matrix is a matrix that maps every single coordinate to every other coordinate. So in this case, you're going to have 100 elements. You're going to have one for each coordinate and how it varies with every other coordinate. And then you take that covariance matrix, and then you take all the points of all the training data as their covariance, and you measure them together, and then you take the distance there. And so now we have these two distance metrics, and that's really useful because we're not just relying on one distance metric, we're relying on two. One that handles non-spherical data sets, one that is very, very fast, one that is intuitively makes sense, and then one that handles things where variables are not necessarily independent. So we take these two distance metrics, and we take the two numbers for every protocol. So say we have in the training set 1,500 protocols. We do this calculation 1,500 times for that packet offset, and we get these two numbers. We have the Mahalanobis distance, and we have the Euclidean distance. And we say if, for example, one protocol, say DNS, has the lowest distance in both metrics, we say that is we're pretty sure that that's DNS. We have, both metrics agreeing. Then what happens if you have, say, each metric identifies the lowest distance for two different protocols? Well, at that point, you have a bit of a conundrum. And we've left it sort of up to the network administrator there, whoever's using our software. He can say, we prefer to just pick the lowest distance. Whichever one gave the lowest distance, that's the one we want. Or you can say, we prefer to always choose the Mahalanobis distance if there's a disagreement. Or we can say, we always choose the Euclidean distance. And then finally, in the incredibly unlikely chance that both of those distances identify two different protocols and the distances are exactly the same, we just go ahead and flip a coin in favor of the Mahalanobis distance. But that way we have with these two metrics, it's great. It's just one more layer that we can make sure we're talking about one specific protocol. We look at all these different things. And can we go to the next slide? Okay. So that slide was, got a little ahead of myself there. But that's just talking about the Mahalanobis distance and how it can handle non-spherical data sets, things that are not distributed spherically around the mean. Okay, Rohit wanted to do this part. This was showing off the new 3D stuff that's all sorts of cool. So I'm going to hand it back to him.
Well, so since we have 10 dimensions, obviously you can't make a plot in 10 dimensions. What we chose to instead do to highlight how the data sets do lie fairly far apart visually is to choose three coordinates, the entropy and the average packet sizes to both the client and server. And what I have here in the next plot, it's not a very pretty looking plot, but what you see is there is a cube for RTP and a cube for DNS, and in this slice of 3 dimensions, both these cubes lie quite far apart. And each point actually on that cube represents a packet trace we have for that particular traffic. So we have had hundreds of thousands of conversations which were recorded for RTP. So all of those points kind of clustered to form that cube there. And similarly, we had lots of DNS samples recorded, and all of the DNS samples lie a little different from there. So at any point of time now, if I want to, as he explained to you, the Euclidean and the other Mahalanobis distance, if I have another unknown trace which comes by, which I know is either RTP or DNS, and I plot it even in this particular 3-dimensional slice, and I find the distance for that trace from these two, I can figure out which cluster it would belong to and figure out which of the two protocols it is.
And so what we've got here is some actual results, which it's always scary to actually show your results. It's never fun, but this actually turned out really well. We were pleasantly surprised. So what we were looking at here is a NetBIOS packet capture, right? And we're looking at what its average Euclidean distance is from everything else. And so we fire this unknown NetBIOS PCAP. We're pretending we don't know what it is. We fire this NetBIOS PCAP through PISA, and it calculates all the distances for all these other protocols. And it says, well, the lowest distance, 676, is NetBIOS. And then you'll note that the next closest guess, which is NTP, was 1,100 units away in the scaled Euclidean, very far away. So we were really, really sure that this is NetBIOS. And that was, when we saw that, this was actually one of the first experiments we ran, we were like, wow, that really works. Man, it's so nice to see an idea go from inception to completion. And that's what we saw when we did this. And can we go to the next slide? There we go. And so we've got Skype once again. And so we're running this unknown Skype PCAP. We're pretending like we don't know what it is. I think it was actually a conversation with Rohit's grandmother. But I didn't know. And we fired it through PISA. And PISA does all these tests and does all its magic and everything. And it comes up with these distance metrics again. And it says that its average Euclidean distance from the Skype cluster, 737. And its next best guess was 972 units away. So it's very, very sure, very, very sure that it is definitely Skype. It's not NetBIOS. And that's really good. And that was one of those things we wanted to make sure we tested with NetBIOS and Skype and all these other protocols, especially the ones that you never, ever want to have misidentified. We really concentrated on DNS, on SMB, all that sort of thing, because we don't want you to have your network policy declare you can't use Skype and then suddenly nobody can connect to the file share. That would be bad. So, and did you want to do the second one?
No, I can. You can if you want.
All right. And so this one was also really, really cool. A coworker of ours does a lot of work with VoIP and steganography. And so we're looking at real-time protocol, right? Real-time transfer protocol. And what he was doing is he's running these experiments to put steganographic information and enclosing it in this RTP protocol and then sending off and hoping nobody notices. And steganography is the hiding of information in plain sight, like having, a microdot or having every third word means something, things like that. But it's still, you have to look for it to know it's there. And that's what he's doing with RTPs. He's doing this steganographic insertion of data. And we wanted to see, wow, wouldn't it be cool if we could tell if he was doing this through statistical analysis? So not even just identifying the protocol, but identifying a protocol anomaly. So you can say, wait, this isn't really RTP. There's something fishy going on here. We should probably investigate this. And so that's what we did. We took, we had this huge training set of RTP and we fired it through. And then we fired through this RTP stream that had some steganographic information embedded. And what we found was that there was a 35% increase in the Shannon entropy. And that's because normally RTP is a very regular sort of thing. It doesn't have a lot of randomness. It's very, very normal. And all of a sudden, when you have all this other stuff that doesn't look like RTP, it suddenly increases the randomness quite a bit. It's not as regular as it once was. And so PISA was able to say, no, wait, this is an anomaly. There's a 35% difference along this axis for this protocol. You should probably look into this. And we were, of course, overjoyed that this worked, and my coworker was less than joyed that we caught him, but, what are you going to do? So he bought me a beer. That's, I guess, what you do. So can we go to the next slide? Oh, yeah, this is going to be Rohit. I'm going to let him finish up here.
So in conclusion, what you saw from various examples being presented for Skype as well as for the steganography is you can use this statistical framework to identify three things. You can identify the obfuscated and encrypted protocols. You can try to go and find anomalies happening over regular ports and regular protocols if somebody's trying to hide information or somebody's trying to do some covert channels. And we have a current version of the code which we will soon post to our dvlabs.tippingpoint.com website. What we would really want is if some of you would start using this particular script for the protocols in your network and also send us more training samples for different protocols that would further enrich actually the signature set we are trying to build, a statistical signature set for various protocols which we are trying to build using this tool.
So that's a dictionary?
Yes, at the end of it there will be a dictionary.
And any protocols that you send us, once they're run through here, they're completely anonymized. It's just statistical information. There's no data, left in there. We're not going to see what you were looking at or anything like that. We just see the statistics about the stream. So, and you could just say this was HTTP or this was whatever, and then we can say, oh, okay, great. There are the statistics for it. We don't actually know what you were doing. It's okay. We won't tell your boss. We won't tell your wife. It's all good.
So thanks.
And now, questions?
So you need to capture...
Yeah, well, okay. Yeah. Thank you. Woo!